It's a free application. You can download it. But if you get a license for it, but you're limited to like 15 minutes. You get the application. If you pay the license fee, you can do unlimited. So we record these classes, and I post them on Blackboard. Inside, I post links for them in Blackboard in that recorded lecture section. But these don't upload automatically. I have to upload the lectures. The only time I usually have to do it is around Friday. It takes longer to upload them than it does to record them. But as soon as I upload them to YouTube, you can see if you go to, there's going to be links. You don't have to follow me on the YouTube. But you can just go to YouTube and search for Rich Raymond, and every lecture that I've ever uploaded will be up there. And so that's what this is right here. Problems. Is I'll leave it recorded. I'll record 2 or 3 hours worth of nothing. Or I forget to take it off pause. And I don't use a microphone. I use the microphone off this. So a lot of times I'll move away from the computer. You can still hear it, but you might have to have headphones to watch it if you're absent. So we'll talk a little bit about. Let me unfreeze the screen. So that didn't do y'all any good, did it? See, I froze the screen while I was registering people. So, introduction to PLCs, and we're going to get a basic introduction to electricity. So we need to understand a little bit about electricity. Some of y'all, this is going to be quite a bit of repeat. Just bear with us. So pretest. There you go. What is an electrical circuit? Can anybody answer that question? Nobody can answer that question? What is a electrical circuit?
It's there's power source. What is it made up of? Or
The basic, but what's the basic requirement of electrical circuit?
the line of electricity follows.
Yeah. What is an electrical conductor? We okay there? What is an electrical insulator? What's the natural metal that is the best conductor of electricity? What are the two most often used electrical conductors? What is voltage, current, resistance, and power? The basic difference between DC and AC, you need to really understand that. What's the cycle frequency in a hertz? What's the difference between an open and a short? What's required for the basic electrical circuit? We need to understand series and parallel circuits. Because we're going to be doing some of that. Resistance and reactance is probably not very important for this class. True and apparent power, we'll probably talk about that.
Is this pretest that you have up there? Is that something you have on our blackboard? Is it where you?
Well, these PowerPoints are up there. Okay. And this is what's going to be covered. So what we should do is by the time we get to that, we should be able to answer these questions, right? So most people, when you say what's the best conductor of electricity, just about everybody says gold, but that's not true. Anybody know what the best conductor of electricity is? Silver is the best conductor of electricity, followed by copper, followed by gold, followed by aluminum. Now, of all these, which one do we use most often? Copper and aluminum. These are the two miles we use. We use silver for a plating. So plating means to coat with. Y'all probably know that if you ever listen to the commercial where these people sell these coins, and they say plated with 3 milligrams of pure gold. So what it does is you take one metal, and then what you do using different methods, you literally put an extremely thin coating of this metal on that. So a lot of our switches, like light switches and stuff like that, where you literally make a circuit by connecting two wires together, usually that point that's where they touch is going to be silver plated. Gold, what advantage does gold have over silver? Most metals rust. We call that oxide. It's a rust. Silver oxide is just as good as conductor as silver, which is very strange. Most oxides don't want to conduct electricity. This is the advantage of gold. What is the advantage of gold over other metals? It doesn't rust. Yeah. So a lot of times you'll get into a printed circuit board or electronic circuit. Like if you took your cell phone apart and started looking at it, you're going to see a lot of what looks like gold, but it's not. It's a gold plate. And what do they gold plate it for? Well, it doesn't oxidize. Copper oxide is a insulator. And copper rusts. So copper is going to oxidize. Aluminum oxide is an insulator. So that means if we're going to expose these metals to the atmosphere, we're either not going to worry about it, or in some situations we're going to plate it with either gold or tin. Tin's very popular now inside computers. They used to gold plate everything inside computers, all the boards, everything that was exposed to the atmosphere, all your connections, all your plugs and everything, you plug everything in. Then they finally realized that they didn't need to do that because computers become obsolete pretty fast, right? You understand that, or what we call obsolete. So now they do a lot of silver, most commonly used as a plating. Copper is extremely good. Gold is very good, commonly used as a plating. Aluminum, commonly used for high voltage conductors. Copper and aluminum are the most often used conductors. So normally we use copper for electronics and something that's going to be real close. Then we use aluminum for high voltage. So just about all your power transmission is done with aluminum. Force. Everybody understand what a force is? What's a force? It's up there, guys.
The interaction that it does
change the motion of an object. Okay, so we have pressure. So what's the difference between a pressure and a force? Anybody know? They're very closely related to each other. So I should put pressure up there too. So what's pressure? Well, yeah, but it's a difference in potential, basically. Pressure. A pressure is a difference in potential. Okay. And then we have to have pressure before we have force. Everybody understand that? So a pressure is what's doing. So pressure is creating the force. That makes sense? And then, of course, if we have a force, it's going to cause things to move. Work. This is transfer of energy from one physical system to another. Well, how do we get electricity? So electricity is a form of energy, right? We get work out. How do we get electricity? Well, we get it from lightning. But how do we get electricity at our house? Well, we take one form of energy and we convert it into what? Another. So we have hydroelectric. So what are we doing there? We're taking one form of energy, taking fluid power or hydraulic power and converting it into what? Into electric energy. We have nuclear, which is still pretty popular, and of course coal, which is a natural gas. So a lot of your power plants are converting over to natural gas. So we take one form of energy basically that exists in nature, and then we do what? We convert it over, and then we make it, once we get energy, then we can make it do work for us, right? So work is a transfer of energy from one physical system to another. It's basically the transfer of energy to a body by an application of force that moves the body in the direction of the force. It's calculated as the product of the force and the distance. So believe it or not, we don't create work. We just take natural work and we change its form. Power. Power is pretty important. So power is the rate of doing work. Power, we call it calories. So when we talk about how many calories you burn, that's power, right? That's the power that you burn. In electricity, this is the primary force we use. So force, to get power, we got to take force, and then we divide it by distance. Distance and speed are the opposite, or we call them reciprocal to each other. So one of our primary forces is this formula right here. So power will be equal to what? Force times speed. Everybody okay there? And if you had intro to if you had intro to engineering, we don't teach power there yet. All we do is we teach voltage, current, and opposition, but we don't teach power. And power is very important because, you know, so to get power, we have to have what? We have to have a force, and we have to have speed. If we don't have a force and a speed, we don't get power. And what do you pay every month? You pay a power bill. You don't pay a force bill. You don't pay a speed bill. You pay a power bill. So power is work. Everybody understand that? So that's what we're paying for. We're actually paying for work. Electrical device operates from, all electrical devices operate from what we call current. We'll learn what current is in a minute. So this is an electrical device and it operates off of electrical. The amount of power produced by these devices is determined by the amount of current that flows through them and the force that is causing the current to flow. So current is speed. So when we start talking about current in electricity, that is speed. That's the rate something's moving. Everybody understand that? And then of course we have to have a force. We have to have a pressure. We have to have a push, right, to create a force. The amount of current is controlled by the amount of force divided by the amount of opposition. Does that make sense? Huh? This is what we call Ohm's law, but it should make sense because how fast something moves depends on how much pressure you got pushing it and how much opposition you're pushing against. So you go out there and you start pushing a car. What determines how fast you can push that car? How much force you can generate, right? Y'all understand? Everybody understand? How much force you can generate. And then that's going to cause it to move. Well, it don't move and you don't actually create work until it does what? Until it moves. You get two people out there, your force goes up, what happens to your speed? Speed goes up. If the opposition don't change. If you change the weight of the car, then if the car gets lighter, you will be able to push it faster. If the car gets heavier, you're going to be able to push it slower. So how much force determined by how much opposition would determine the speed that you can push that car. Does that make sense? So the amount of speed is controlled by the amount of force divided by the amount of opposition. So that would be how fast you can move the car would be how much force divided by the weight of the car. So if the weight of the car goes up, speed goes down, right? You understand? If the weight of the car goes down, speed goes up. If you come over here and you push more force, if you don't change the opposition, then the speed's going to go up, right? You understand? Electrical current consists of atoms, electrons, that have been forced to move by a difference of electrical potential. And that difference in electric potential, which is our force. Voltage is a pressure. We can't have force unless we have pressure, right? You understand that? So voltage is a pressure. It becomes a force when we allow it to move against something. Everybody understand that? So I got my battery sitting out there in my car. I go down the AutoZone and I buy a new battery. That sucker's generating a pressure. It's not generating a force. Right? You understand? Until I go in and put those wires in my car, right? You understand? Then all of a sudden that thing's going to be generating, it's going to be generating a force because now if we got opposition, we're going to have something that's moving. And what's moving? Electron. Batteries do not produce electrons. All the battery does is move the electrons that's already there. Everybody understand that? It's just like a pump does not create water. What does a pump do? It pushes the water that's already there. So all these things that we got is made up of electrons. Everybody understand that? Wires are made out of electrons. Light bulbs are made out of electrons. And all the force does, it creates a difference in potential. Now we have a pressure, right? You understand? We've got something that we can push that again and we generate a force. The strength and difference of the electrical potential voltage and the amount of opposition to the flow of electrons determines what speed the electrons move. And speed, we rate that in something we call what? And that's even in water. When we talk about current in water. That's how fast the water is moving, right? You understand that? If it's sitting there stagnant, we don't have a current, right? You understand? Everybody okay? Some materials, such as metals, allow electrons to move freely, while others, such as rubber, don't. So we have different categories. We have what we call conductors, and then we have what we call insulators. Now, of course, we would fall into the category of something called a semiconductor. So I would conduct current. So if I get across a voltage source, then there is a path. We've got push, we got force, we got motion. So we push current through our body, which is not good because your brain controls your muscles with current. Also, when we push current through resistance, we get work. Most of the time, that work is in the form of heat. So you start getting current flowing through your body. Your body is not a conductor. Your body is not an insulator. It's going to be what we call a semiconductor, carbon-based. So I'm going to create work, right? You understand that? And this is going to be in the form of heat. Are you what's your name? You supposed to be taking PLCs? Okay. We're about to probably re-register you in the class because William?
Yes.
Oh, here's the syllabus brief. And we recorded the syllabus and everything online. I'll get you. You're not on the roll. When did you register for the class?
Well, they took me out and they just put me back.
Okay.
Thank you.
So that means if I've got these chunks of metal out there, and I get into those chunks of metal, and it's a path for current flow, then I can get current through my body, right? You understand? So what we do is we coat these conductors with insulation. These are going to be usually Teflon or something like that, something that has an extremely high resistance or opposition to the current flow. If they don't have the ability to get in contact with something, or if the push is low enough, sometimes we don't coat. So you look at your power lines, these guys are using air as an insulator. Air is a pretty good insulator. So a lot of your power lines don't have any coating around them, right? You understand that? So you got to be real careful around those things. Because air's an insulator. Air's a real good insulator. If it wasn't, we would have a lot of problems. Because power lines don't use insulation. And you got push. And if it's got a path, it will push something through it. Even insulators, a lot of people think there's no current flow through the insulator. But if we've got enough push, if we've got a difference of potential, and we push that against something, if there's a path and there's current flow through the insulator, it's referred to as a volumetric current. But it's so dang small that we don't have the ability to measure the current flow in the insulator. but it drops anytime you push current through an opposition. You lose push. So what happens is all your push is lost inside the insulator. We'll look at that in a minute. Paper, rubber, Teflon, all these make real good insulation. Air makes a good insulator too. Of course, we can't get them real close because the problem with air is its resistance varies quite a bit. So when it's raining, its resistance goes down. When you get into those high voltage lines, those conductors are really, really spread apart. Voltage. So voltage is a difference in electrical potential that forces electrons to move if there is a path. So if air wasn't a good insulator, an extremely good insulator, your batteries would run down all the time, right? Don't understand that. Everybody okay there? Current is the flow of electrons that results from a difference in electrical potential. And of course, we got to have a path, which said that. The resistance or reactant, this is the opposition to the flow of current. So one thing, I can't create work unless I push against something, right? You understand that? You understand that? And what we're going to push against is going to be resistance. And when I push against that resistance, it's going to create what? It's going to create work. But to get work, we got to have the current, right? You understand that? So we got to have a force, and we got to have speed. So an electrical circuit is defined as a complete path for current. A basic circuit consists of conductors. It's just like your body. Your body is a lot like an electrical circuit. So we got a heart. What does a heart do? Pumps blood, right? Sends it out through arteries. And where does it go to? Goes to muscles. It carries all this energy with it, right? You understand? Then it goes through the muscles. And then what do we have to do with it now? We have to return it, right? You understand? Bring it back. We have to go through the lungs to re-aerate it and put different, well, we bring it back through veins. So out with arteries, back with veins. So if you lose that path, then you got problems, right? You understand? This is what causes strokes and that kind of stuff. And one of the things, main things they do, when you go to the doctor, what's one of the first things they do? Besides look at your height and your weight, they check your pressure. Make sure you got that right pressure to push that blood through your system, right? So what we have to have a minimum of something that pushes. And this is what we call our voltage source. Then we got to have two conductors. We got to have one that supplies the current out to the load. Then the current goes through the load does the work, and then we do what? Then we bring it back to the voltage. Everybody okay? A good analogy, of course, is the human circuitry. There's a mouthpiece. Which one of these you are? Electrical circuit works similar to the human circulatory system. So the heart pumps blood through arteries, through the muscles, back through, I forgot the lungs. Back through the lungs, through the heart, right? Everybody okay? Any questions so far? So the voltage source is similar to the heart. So the voltage source does not create electrons. Everybody understand that? So what does it do? Movement's already there. So your loads already have electrons out there. Your conductors have a bunch of them that can be moved, right? You understand that? And then the voltage and your battery has electrons in it. So it's just that's all it is. It's nothing but a pump. That's all a voltage source is a pump that moves everything that's already there. Electrical conductors are similar to vessels, and then your muscles are similar to the loads. Everybody okay there? So this is the basic, these are two basic circuits. But here we have a battery. Then we have what? We have a conductor. Now a conductor, we want it to have, we would love for it to have no opposition. But that's not true. All conductors have some opposition. And that means they do work, right? They'll do work. But they have almost no opposition at all. In fact, the opposition in electricity, and we'll look at that in a minute, is rated in something called ohms. And the higher the ohm value, the more opposition that you have. Conductors are rated in, they're rated in ohms per kilometer. So, that would be almost no ohms for a certain amount. And we'll talk about what determines that amount of ohms too. So we have a what we'll call a source conductor. And then we have what we'll call a return conductor, and here's our load. What supposedly does all the work? The load. Unfortunately, the conductors do some work, not very much. So when we push that work, that current through this light bulb, now it's going to take that energy and convert it into what? Into light. Voltage source, source conductor, electrical load, return conductor. And then when the current flows through the load, it does what? It does work. We have three ways we can hook circuits. We can hook what we call series parallel and series parallel. Now the two we're going to use in this class are series and parallel. And they're not going to be very complicated series circuits. They're going to be one load with one load circuit. So we're going to do one load simple circuits and parallel circuits. I'm not going to do anything. But we'll show y'all just an example of it in a minute. Series circuit consists of one or more load connected one after the other. The voltage provided by the source is distributed. So what happens when we run? So the voltage source don't move. Everybody understand that? It's sitting back over. Your battery does not move. But what happens? It's just like, so your heart does not move. But what happens is we push that blood out, and then it goes into an opposition. So what happens when it goes to an opposition? Well, what happens is we lose some of the push. And we call that a voltage drop. Everybody understand that? So wires have what we call a voltage drop. Electricians or linemen call it line loss. That's how much push you lose in the lines. And they try to keep that to a minimum. Well, attenuation is another term for loss. Usually attenuation, we don't use that in power, we use that in communication systems. Attenuation is a signal, it's not a power loss, it's a signal loss over distance. That's what attenuation is. That's a good point. Voltage provided by the source is distributed across the load proportional to the load. So that means the more opposition a load has, the more pressure drop we'll have. That makes sense. So if we've got a load, 100 ohm resistor connected in series with a 1,000 ohm resistor, then the 1,000 ohm resistor will drop more pressure than the 100 ohm resistor. Does that make sense? Everybody okay so far? Since there's only one path of current through each load is the same through the circuit. So this would be an example of a multi-load series circuit. So it would be proportional, the voltage the pressure, and what happens in this circuit, by the way, if we consider the conductors drop no voltage. So this is the conductor right here. So what we do is we have individual. So what is the function of a conductor? This connects. What's the purpose of your blood vessels? What's the purpose of your blood vessels? Okay. To connect the blood coming out of your heart to your loads, right? You understand? So the function of a conductor is that's its function in life is the conduct current from the voltage source what? Through the loads. So what that would be a conductor. This would be a conductor. This would be a conductor. This right here would be a conductor, and that right there would be a conductor. Now what happens is when this current comes flowing out in this direction right here, and it goes through that load, what are we going to do? Well, we're going to lose some pressure. Now the amount of pressure that it loses would be, so let's say this has 100, and that we use omega to represent ohm. So which one will we lose the most pressure in? Yeah, the 400. Right, you understand that. The 100 would drop the least pressure. And then, of course, here I just increased as we go around. If they all had the same ohm value, then each one of them would lose the same amount of pressure. Does that make sense? And what happens is all this pressure is gone before we get around here. So this guy right here would drop 1/10 of the voltage. This guy over here would drop 2/10, or that would be 1/5. This guy right here would drop 3/10, and this guy right here would drop 4/10, because of the ratio between the other resistors. Now y'all learn that in series circuit. But what happens is by the time I get back here, if I was to come over here and establish a reference point to measure this, so we have a meter that we use to measure difference of potential, and we call it a voltmeter. And the voltmeter has two leads on it. One of them is going to be black. So what we do is we establish one of them as our common, and then my meter would be here, and then it would come over here, and I need to draw this in a different color. If this is DC, this right here would be the red lead. So the meter is going to have two leads on it. And this right here would actually be red. Now, if this meter, so what we do is we rate these things in how much push is available. So a car battery, how much push is available? 12 volts. So if you went out there with your voltmeter and put it across your car battery, when your engine's not running and it's been sitting overnight, you put it across the car battery, it should measure 12 volts. Makes sense? When your engine's running, lead acid batteries are put more voltage on them than they're rated at. Around 14.3, right around there if the car is running. And then as soon as you turn it off, it'll probably drop down to around 13 volts. And if you let it set overnight, it's going to measure what? It's going to measure about 12. So right now, if I put my voltmeter across this, I would measure 12 volts. If I come over here, this guy here is going to drop what? 1/10. What's 1/10? It would be 5 volts. So this guy right here would measure what? It would measure 45 volts. That makes sense? And then I come around, and then I come around, and I come around, and when I hit back here, I would be back at, if I put my red lead right there, what's it going to measure? It's going to measure 0. So what that means in a series circuit, all the voltage is distributed in the circuit. It's dropped in the circuit. So if you took a meter and you put it on your black post and went back to your black post, your meter's going to measure 0 volts, right? You understand? Now, the problem we have with a series circuit is that if something happens, you come over here and you take this load right here out and you don't reconnect the wires, then what happens is we've lost our path for current flow. If we have no current flow, we have no work. You understand that? We call this an open circuit. So this is why if you got Christmas tree lights, you go out there and you pull out one of them, you're going to lose what? You're going to lose a set of them because they're connected in series. But you plug those suckers into 120 volts, those light bulbs are not rated at 120 volts. They might be a 3 volts because they all have the same resistance, and each one of them only drops the voltage that's required, right? You understand? You go out there and one of them goes out and you get a piece of aluminum foil and put it in the socket, you notice all the other bulbs get brighter. And why? Because it's lost that load, right? You understand that? And of course now they blow out easy. So the big advantages of a series circuit is that we distribute the loads around the circuit. The biggest disadvantage is if you lose one load, you lose all of it. Because you lose the flow. If you lose the flow, so we could have a force, but if we don't have the speed, we don't have what? We don't have work. Now we're not going to have a series circuit. We're going to have series circuits, but our series circuits are going to look like this. So here's going to be my voltage source. Here's going to be my load. And here's going to be a rubber terminal. So we're going to have a one load series circuit. So these are the only loads we're going to have in PLCs and also in motor controls. So those are really, probably if you take PLCs, you probably need to take motor controls too. And we'll talk about the difference between a PLC and motor control. So you know your house is not wired in series, because what would happen if your house was wired in series? What would happen if one of your light bulbs blew out? That everything in your house would go out. Everything would go out, right? So we have another method of wiring that we refer to as a parallel. This is parallel. All the voltage applied to each load is the same. All loads are connected across the voltage source. The current is distributed in the circuit inversely proportional to the branch opposition. So this is a parallel circuit. This is your house. This is Alabama Power. They distribute power in parallel. So how much current that flows to this load has nothing to do with the current that flows to that load, which has nothing to do with the current that flows to that load, which has nothing to do with the current that flows to that load. You don't understand that? Because the voltage is the same. So this is the way your house is wired. And of course, our voltages are different. National Electrical Code says that standard voltage at the house is 120 and 240. And we'll talk about why we have two different voltages. So that means every one of these devices have 120 volts across. Now, if this guy right here is conducting 5 amps, and this guy right here is conducting 4 amps, and this right here is conducting 3 amps, do we know what an amp is? This is the way we rate the speed of the currents. So it's like in cars. What do we rate our speed in our cars? How do we do our miles per hour? Well, what we're doing here is we're doing electrons per second, and it's 6.82 times 10 to the 18th electrons past any point in the circuit in a second. Now, what would happen? Let's make this 2 amps. If I add all this up, so what would that be? That'd be 9. That would be 12. And this is 2. That'd be 14. And what your power source is providing is having to provide all 14 amps, right? You understand? It's just like all the cars going to Birmingham. We have some go this way, some go that way, some go, but they eventually all end back up at Birmingham, right? You understand? So if I was to have the ability to measure that current there or measure that current here, it would measure 14 amps. If I came over and measured it right there, it would measure 9 amps. Because what's happened is that this current's like that, right? You understand that? Everybody okay? And then of course this would be 4 amps less, this would be 4 amps less, this would be 4 amps less. But it all will, if I added that right, it would all work up to what? Did I add that right? Is that 13? That's 5, 10, 18, 19, right? What did I say, 19? Or did it say 2 right here? 2. So what would that be? That'd be 9, that'd be 12, that'd be 14. Now what would happen is if I come over here and take this load out right here? Well, this right here would drop down to 12 amps. Y'all understand that? I took out this last load, it was just 2 amps. So what happened is that the amount of work being provided by my voltage source went down, right? You understand? Because it's having to provide this current. So this is why you tell your kids or everybody in your house, your mom tells you that turn off the light. Because when you turn off that light, you take away a current. If you take away a current, you remove some of that power that's being produced, right? So in a parallel circuit, what's nice about a parallel circuit is we can add and remove loads, and it does not affect any load in the circuit. We can turn lights off, we can turn them on, we can turn on air conditioners, we can turn them off, we can turn heaters on, we can turn them off. Of course, the less stuff that you run, the less power your companies, the power companies having to provide. But we can add in, I can unplug things. So all you got is you got these plugs out there. You go in and you plug something in. All you're doing is adding another load. You plug something in. You're just adding another load out here. That's all it's doing. That's all you do is add another load. So we're going to have plenty of parallel circuits. So the two circuits we're going to run in here in PLCs and in motor controls, we have two circuits available to us. We have a single load, a series circuit, and we have a multiple load parallel circuit. That's the only two loads available. The only time you'll run into true series circuits, series circuits, you run into them in Christmas lights, right? You understand that? And in electronics, we use a lot of series circuits. Probably the most popular in electronics is something called series parallel, which we won't even. What do you think series parallel is? So this is what Christmas lights are now wired in series parallel. So what happens now when you go out and you pull out a light bulb? Do you lose all the light? No, you just use a little section of them. Well, all those are wired in series, right? You understand? But it's also what? Parallel. And this is the way your Christmas lights are, series parallel. So that means if I come over here and lose this load, I lose the current path through here, but I don't lose the current path over to these bulbs over here. So most of your Christmas lights now are series parallel. And you'll definitely run into these in electronic circuits. We will not have series parallels in motor controls, and we don't have series parallel circuits in PLCs. Everybody okay? But we do have control devices, so we need to have the ability to control this current. So what can I do with these lights right here? I can turn them on or turn them off. Okay, we can do this with our TVs. So definitely we need to have some way that we can control the current, flow of current. We need to have some way that when something happens, and so if I was to come over here and accidentally touch these two wires together, that's bad. So now the only thing that's limiting the flow of the current is the resistance of the wire. Now if the wire has no, so if I say the amount of, so we have something called Ohm's law, and this is where we can calculate the amount of current, and we take that, so I is equal to V over R. And this would be the way we calculate current. So what happens when R goes up, what happens to I? It would go down, right? You understand? But when R goes down, what happens to current? It goes up. Right here, we would have almost no resistance at all. So if the wires had zero resistance, then the current would mathematically go to infinity. But it can't. For one thing, all your voltage sources have opposition. So this is why you got a little old, AA battery. You put a wire across it. If you have your voltmeter across it, you see it go. The voltage goes to zero. Well, what's dropping the voltage? Well, the internal resistance of the battery is dropping. The internal opposition inside the battery is dropping. Right? No understand that. But there's still going to be a lot of current flow. Anytime we push current through resistance, we create work. So the wires get real hot. The voltage source has enough current capability. What do metals do when they get real hot? They melt. Plus, they call fire too. So a lot of our fires in our house are caused just by what we call short circuits. So we need to have something that has the ability to detect when the current flow in the circuit shoots way up, right? To prevent our wires from getting red hot and melting. So what do we call these devices? overloads. We call them overcurrent protection devices. Overload is another thing that we use, but it's got another term. Mainly in your house, you use something we call circuit breakers. And these are devices that automatically come over here and create, it's a control device that creates what we refer to as an open circuit. So, and a light switch, that's what it does. So this is a basic circuit. So we have three things in most circuits. We have a voltage source, we have conductors, we have a load, and then normally we have some type of control device, right? So this is what you're doing with your light switch. You're creating what we call an open circuit. An open circuit in electricity just means you don't have a path of current. So a circuit breaker is like a switch. It's like a light switch, but it automatically opens when a certain current is exceeded, right? Fuses do the same thing. But fuses actually, we call it, they blow. So what's nice about a circuit breaker is you can do what? You can reset it. A fuse, you have to do what? Replace it. So what advantage does a fuse have over a circuit breaker? Go down to Lowe's and look at a 15 amp, 120 volt fuse, and look at a 15 amp, 120 volt circuit breaker, and look at the difference in the prices. You're talking about a few cents for the fuse, and quite a few dollars for the circuit breaker. So circuit breakers cost a lot more money. So when you get into industry, you're going to run into a lot of fuses, a lot of them. Some circuit breakers, houses use a lot of circuit breakers to prevent people from jumping out their fuses with aluminum foil. So control devices, guys, we got switches, all kinds of switches. We have sensors. Sensors take physical quantities and convert them to electrical quantities. Exactly what your sensors do. So your brain does not understand touch. Your brain does not know smell. Your brain does not know sight. What we have is we have these sensors in our body, right? You understand? And what do those sensors do? Well, it takes physical quantities and converts them into electrical quantities that goes into your brain. So your brain processes, it's a computer, it processes electrical quantities. So what does sensors do in control? Well, control, it takes physical quantities, converts them into what? Electrical quantities, so we can process them with electrical information. So when we go over and look at the manufacturing lines today, we'll see tons of sensors. So automated manufacturing is sensors. Because you can't automate something if you don't know what's going on out there, right? You understand? Now what we're going to do in this class is we're going to simulate switches, sensors. So our so this is one of our PLCs. This is a Micrologic 1000 PLC. This is the train. So what we have over here is we have a bunch of lights and we have a bunch of switches. So in these situations, lights are going to be our loads, and the switches are going to be our control devices, right? But what you got to understand, we're going to be manually flipping switches, but automated systems is going to be something else flipping those switches for us automatically, right? These are what we're going to call sensors. We have a class in sensors, which is pretty good. We'll run into sensors a lot in motor controls. So that little guy in the center, this right here is a programmable logic controller. So we have sensors, we have what we call relays, which we're going to get very familiar with in this class. We're going to have push buttons, we got lights. In real life, we would have motors, we would have actuators, we would have all different types of things that we're going to be that's going to be the loads in our circuit. Everybody okay? So you see all these switches and all this kind of stuff mounted on here. This is what we're going to do, by the way. We'll look at this in a little while, and we'll look at a circuit. This is what you do in motor controls. So motor controls requires, this is motor controls. PLCs, we're going to come in and replace a lot of this stuff up here with a computer program. So, typical electrical loads, we're going to have light bulbs. We have what we call actuators. Anybody know what an actuator is?
We use actuators on a plant.
What do they do?
Generally, you use them kind of like a hydraulic pump, and up pushing from from wherever your actuator is out and back and forth.
Okay, but what the actuator is doing is it's taking a pressure and converting it over to motion. That's what an actuator does. So current cannot cause something to move, but we can take that current and push it into an actuator, and then that actuator uses that current and causes something to move. So an actuator is what's converting one energy source into another. But actuators create motion. So you go out there and you hit the little, you pick out your mode on your car, you hit that little thing. Your battery is not opening and closing that door. It is an actuator. It's taking that electrical energy and converting it over to motion. So that's what actuators do. We have some actuators. We have what we call linear actuators and rotary actuators. So that makes sense. So what does linear mean? Anybody know what linear means? Straight line. So we have linear actuators. So these guys are going to push things. So you're talking about the hydraulic cylinders out there. Those are linear actuators. And then we have rotary actuators that create things in an arc. This causes a motion in an arc. So a motor is an actuator, but a motor has its own name. Normally when we use rotary actuators, this is something that's got a limited motion. So it would have stops, it would have mechanical stops, and the arc can only go so far. A motor is an actuator that has no limits. So it would do what? It spin as long as you let it spin. So a motor's got its own name, even though it is technically an actuator. So your actuators are going to be your loads. So we have these things called relays. So what's the problem with the light switch? Who hasn't turned it on and off?
Manual.
Yeah, there's a manual. Industry would be in a big, big problem if guys or people had to go out there and do what? Turn things all on and off. Man, that would be awful. Can you imagine Mercedes doing that? A lot of jobs, right? But and cars will be costing $1 million instead of even though they are very expensive. So used to when they was paying people, pennies per day, they could afford tons of labor, but now we can't afford it. So what we do is we have electrically controlled switches. These are called relays. I'll get one over here that's opened up so you can actually see it. So this is a relay, but the problem is over time they realize that we don't want to expose people to a lot of current and voltage, so they seal them up a little bit. Before that, they didn't seal them up a little bit. So what we have is we have what we call electromagnet. I got one in my computer bag, I believe. So we have something called a solenoid. Anybody know what a solenoid is? This is a solenoid.
It's like a coil.
Yeah, y'all understand electromagnets?
More of that. Magnetically bring us to the switch.
Yeah, when we put current, one of the side effects of pushing current through conductors is that it generates a magnetic field, which is pretty neat. Let me see if my camera. Let's see if I still got my camera. Yes, I do. I'll get this over and see it. So this is a special wire. This is called magnetic wire, and all I've done is I've came over here and just took a bunch of wire and I've wrapped it around a chunk of metal. Let me go full screen with this. Right, here it is. Okay. So all I've done is I've taken a chunk of wire as soon as I find myself, and I've wrapped it around just a bunch of metal. Now this is a special wire called magnetic wire. The insulation on it is extremely thin because what we're trying to do is make sure we couple the magnetic field from one wire into the other. So anytime we put magnetic fields in the same direction, then they're magnetic fields combined, right? You understand that? Then I've got a DC power supply right here. And I'm sorry I didn't bring any jumpers. So this is going to be kind of complicated, hard to do. And then I'm going to find something metal, like it's nailed. Let's see if I can jam that in there. And then all I'm going to do is just come over here and hopefully this works. I'm going to turn the power on, turn the power off, turn the power on, turn the power off. So that's all I'm doing. And y'all seen these a lot. You know, you see these big cranes that do nothing but go out and pick up metal. That's all they are, just big electromagnets. Okay. But let's see what happens. So that's an electromagnet. Now what advantage an electromagnet has over a regular magnet is we can't turn those things off and on. So electromagnets, we can turn them off and we can turn them on. And not only that, is I can vary the strength of the magnet by changing the amount of push I have into that. So I can control it by the amount of push I put on. So the bigger the voltage, the more field we can generate, but you got to be careful. You just can't, because the wires are conducting current, and the only thing that's limiting the current now is the resistance of this wire. So that's why you'll see these electromagnets, they have a lot of wire, and it's very small size wire too, to get enough resistance from the wire so it don't burn it up, right? You understand? And this right here would get hot if I did it. Well, let's say I take this same thing, and what I've done here is I've got a bunch of wire wrapped around a straw. Now, let's see if I can do this again. Normally I bring alligator clip jumpers over here. And what I'm going to do, hopefully, is I'm going to come over here and I'm going to take this nail. I'm going to insert it into the center of my straw. And I'm going to turn my power on. I just created something called a solenoid. This is the solenoid. That's all this is a solenoid. How many places do y'all see solenoid? Well, if you got a washing machine, you got a solenoid out there. How do they turn it? How do they electrically turn that water on and turn that water off coming into your washer? How do they do that? They do it with a solenoid, right? You understand? Everybody, a lot of water fountains run off solenoid. You go up to the UAB. I've spent a lot of time at UAB, by the way. I had a motorcycle wreck back in 2008. A bad one. I'm lucky to be here. But I saw a lot of, I had tons of tests run, and they put me in my bed and rolled me around. And a lot of places, they had limited access to different places. And what did the nurses or interns do? I mean, they just put a little badge and they swiped it over there, or they entered a code. And all of a sudden you heard something go, and they could go through that door. What was locking the door? Solenoids. So these are linear actuators, but these linear actuators, these don't use what it uses is electricity to create an electromagnet. The magnet causes a rod to move, and when that rod moves, it's going to open, close doors, right? It's going to turn on your ice maker in your refrigerator, turn your ice maker off. If you got water in the front door, it's going to turn that water on so you can get water out of there, right? It's going to turn the water off and on coming up electrically. But what we're doing is this is an electrical actuator, right? So what if we take that thing, that same solenoid, and we mount contacts on it? Oops, sorry guys, where's it at? So here's the solenoid right here. Right here. Here's the two wires that'll hook up the solenoid. This is that plunger that was my nail right here. We refer to it as an armature. So when I come over here and put power across these two terminals right here, it's going to suck that thing up like that, right? You understand? Everybody okay? Well, look what I have at the top of these things. I've got switches. So when I come over here, notice here's a switch right here. Can y'all see it? So I'd hook one wire right there. I would hook another wire right there. And when I put energy, these switches come up and they close against each other. And then when I take the power apart, what would they do? They would open. Now, if we look at this set of contacts over here, or switches right here, these are already closed. So right now, with no power on the solenoid, this switch would be closed. And when I come up and do it, this switch right here open. So we call these contacts. We don't call them switches. We call them contacts. And we have what we call normally open contacts. So this would be this would be normally open contacts. So if my solenoid is not energized, these contacts would be open, so the light switch would be off, right? You understand? Over here, these contacts right here are closed, so those lights would be on. So when I energize this solenoid, then these contacts change states. This is what we call a relay. And it's an electrically controlled switch. And we can have multiple contacts on it. So we can control a lot of things with one set of solenoid cord. So this is automation. So if I'm going to automate something, that means we're going to have to put it under control of electricity, right? Now, what can you do with electricity? Pass that one. This has got 1, 2, 3, 4, 5, 6, 7. This has got 8 sets of contacts on it. Some of them normally open, some of them normally closed. So now I can electrically control that switch. So I can electrically turn things on and turn things off. And so now we can do what? We can take that out of the hands of, now eventually somebody's going to have to start this and stop this. Even in pure automation, we have the way of turning things off and turning things off and determining when this sequence starts, right? You understand that? It's just like airplanes, current airplane. Most of your new commercial airplanes have the ability to land themselves, but they still have a pilot in that seat, right? In case what? Something goes wrong. So relays. So what we're going to deal with is we're going to simulate relays, but I'm going to show y'all some things here in a minute. Let me get back to the PowerPoint. Everybody okay? We'll take a break in a minute. Guys, I went too far. I went too far again. Why is it doing that to me? Oh, I know why it's doing that. There we go. What we do though, when we get into circuits, everybody okay with what a circuit is? Everybody okay? Everybody understand voltage, current, and opposition? Everybody okay with that? Everybody understand control, some control. And it shows y'all a relay. When we start drawing diagrams, so if I'm going to figure out how circuit works, we need to come up with a way, instead of me having to physically draw. We have a type of drawing called a pictorial diagram. This is kind of like you get when you go out and buy like a new TV. And you go in and shows you how to hook everything up. What do? They draw pictures of everything, right? And you can see how complicated that can get. So what we do in these trades, in these different trades, is we come up with these different diagrams where we don't draw pictures of the items. We use a symbol to represent the item in the diagram. Okay, does that make sense? So what we need to do when we get into this is we need to learn symbols. Because the diagrams are not going to, odds are, they're not going to be pictorial diagrams. They're going to be diagrams for a trade. So even carpenters, when they go out and build houses, you know, they don't have a picture of the board. They don't have anything like that. They have a diagram, and each symbol represents things. Electricians, when you go out and wire houses and do commercial wiring, you know, they don't draw pictures of plugs and panel boxes. They have symbols that represent that kind of stuff, right? Don't understand that. So symbols, we have symbols of the trade. Huh? We used to call them blueprints, and there's still a lot of them call it that. Some of your old school people, but each diagram has names. So in electronics, what we do is we call them schematics. We have schematic diagrams. We learn all these symbols, and we're not going to look at much of them. So this is some of the symbols that we would use in electrical. So we have a DC voltage source. So we have two types of current. We have direct current. This is current that's flowing in one direction. Then we have alternating current. This is current that's constantly going back and forth, 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 back and forth. Now, why do we have two? Well, there's got to be a reason. If one didn't have an advantage over the other, we wouldn't have the other. So what advantage does one have over the other? Anybody know? Well, direct current, we can electronically control direct current. So direct current is easy to control using electronic devices. AC is what we transmit power. So AC is more efficient to transmit power. So this is why Alabama Power transmits AC and not DC. We can do something with AC that we can't do with DC. We can do these things right here. This is a symbol or something called a transformer. Everybody know what a transformer is? Huh? It does two things. One thing a transformer doesn't do, it's a power source. So it doesn't change power. So if these transformers were 100% efficient, that means I go at my house over there, or here. This is TVA, Tennessee Valley. So the power generating companies for this college is up in the Tennessee Valley. So this is not Alabama Power. This is TVA. They've got to be able to get that power from the Tennessee Valley down to that's when through conductors. And conductors have resistance. If you put current through resistance, you have a line off, right? So what we can do with AC that we can do with DC is we can step the voltage up and we can step the voltage down. But we're not changing the power. So technically, we turn on this light right here, and it's, I don't know how many watts, just an example, let's say it's 200 watts. Well, that power company that's providing this would have to give me how much power? 200 watts. It's going to be more because the transformers are not 100% efficient. Well, if we assume that all your transformers and everything are 100% efficient, that means you go on your house and you turn on a 100-watt light bulb, the The power company gives you 100 watts. Everybody understand? Now, what did we say power is equal to? We said it's equal to force times speed. So on electricity, power would be equal to the amount of volts we have, which is V or E, times I. Everybody understand that? So we have this little formula that y'all are going to learn. We call it any three terms. So, you know, you could transpose this. And what we're going to do is we're going to solve for I. So you can multiply, divide, do all that kind of stuff. But when you got a three-term expression like this, especially multiplication, what you can do is you can put what you're solved for on the top. Then I'm going to put a line, and I'm going to put V, I. And now I can transpose this equation just by looking at this. So what I'm doing is I'm looking at this guy right here. So I would be equal to P over V. This is the guy. This is Alabama Power right here. So I'm trying to give you a certain amount of power. Well, if I raise that voltage up, what happens to this guy over here? It goes down. Well, what determines how much voltage drop you get in an opposition is the amount of voltage drop is equal to I times the amount of opposition we have. So that means the lower the current, what happens? Huh? The less voltage drop we have. I can't change the ohm of the wire. So the lower the current, the less voltage drop we would have. So if I can step that voltage up, if I can increase that voltage, not changing the power, if I can increase that voltage, the higher I make it, the less loss we would have in our wires. So that means if I could get that voltage up to 750,000 volts, that means I could send 750 watts of power with 1 amp. Well, what's the problem? Well, I couldn't get 750,000 volts down toward what it's looking for. It's looking for ground, right? You understand? And if you got into 750,000 volts, it'd be like that guy on Eagle Eye. Y'all see the movie Eagle Eye? Where those high tension lines fell down on him? What happened to him? He just disappeared. That would be the truth. So the problem with high voltage is it's more efficient. It takes less current to develop that power, but the higher the voltage, the more dangerous it is. So what we can do is we can run it through a transformer and step the voltage up extremely high to transmit it. But then when I start getting down toward you, I'm going to have to start doing what? Stepping it down to make it what? Safer. And the closer we get to ground, the safer it has to be. So what's the two voltages we run in our house? Yeah, NEC says 120 and 240. Of course, it's probably not going to be that, right? But it's going to be close. What do we use the 120 for? We're 120. Which one's safer? 100. What do we use 120 for? For your low power devices. All your low power devices. What do we use 240 for? Your high power devices. Where the plugs are at 240, anybody can get to that? They're either hardwired, right? You understand, or they're down below on the baseboard because they want to keep you out of those things. But what you have to understand, loads are designed around a certain power, right? You understand. So you can't take a 240, a load that's around 240 and hook it up to 120. You produce 1/4 of the power. Or you can't take a load that's designed around 120 and run it on 240 or burn it up just like that, right? You understand? So loads are designed around a certain voltage. So what can we do with AC that we can't do with DC? We can step that voltage up for transmission. We can step it down for what? Safety. So that's the big advantage of AC. Plus AC motors are cheaper because we can work off induction. What advantage does DC have over AC? Well, that's not the advantage. We can electronically control it. So I can make DC do this. I can make DC display this picture up here on the screen. I can make this computer right here run this thing. This computer does not operate off of AC. It operates off what? DC. So I have these things. What do we call these? We call them power supplies. So your TV has a power supply in it. So electronically, DC we can electronically control. Y'all understand that?
That's the transformer. How does the transformer not change at all?
Because work in equals work out. That's true. We don't create. We never create power. We take power, one source of power, and we change its form.
So the transformer that have to set. Change and adjust.
Both.
Step down the voltage.
Yeah, but it changes the current. So what happens, the more if you're delivering power over here, if you step the voltage up, the current goes down to produce that power. So a lot of people say, what does the transformer do? Well, it steps the voltage up or steps the voltage down. But if it steps the voltage up, the current goes down. If it steps the voltage down, the current goes up. So current and voltage are inverse of each other. What's inside? It does it through magnetics. So what happens if I take a conductor, if I was just, and we got it right here. Let me pause the lecture.